All right, we are picking back up where we left off in section 1 of chapter 5. We looked at some of the fundamental identities, trig identities in the first video, and used those along with some algebraic skills to simplify some trigonometric expressions. Now what we're going to do is we're going to look to see if we can use those to help us to verify or prove that an equation is an identity. Now remember, an identity is an equation that's true for all values of the variable for which it's defined. So we're going to use these general steps here, and this is very general here as I have described. Step 1, work with one side of the equation. And typically the best one to work with is the more complicated side. But at the same time, make sure that you know what the other side is of the equation, and kind of keep that in mind as you're working towards making one side equal to that side as your final goal, as I have written down. Also, this is where we're going to use the different fundamental identities, and of course this is when the occasion arises to use the fundamental identities. For example, if the expression is a product or quotient of factors, consider using the reciprocal and quotient identities. If it has square terms, look to see if the terms can be grouped to match up with one of the Pythagorean identities. Where the expression involves a negative argument, like a negative variable, a negative angle, consider the even and odd identities to see if you can simplify that. Now once you've done those kinds of things, you also have to remember you're going to use some algebra. You might have to use some factoring, you might have to multiply factors, combine like terms. You might want to try to write rational expressions, fractions, so that they have a common denominator. And if all else fails, and this is my go-to guy when I'm not really sure where to how to get started, a lot of times what I'll do is I'll rewrite the expression, changing all the trig functions into terms of sine and cosine. Alright, now that's just really general terms. It doesn't say do this first, do this second. These are things that you should keep in mind as you're verifying identities. We're going to do a couple of them right off the bat. We're going to do more than two, but we'll start off with these two. It says verify that the equation is identity, and for the first one here, A, the sine of the opposite of x times the cosine of the opposite of x, excuse me, the cotangent of the opposite of x, all divided by the cosine of x is equal to 1. I notice here I have negative arguments. That's what this is talking about. Negative arguments means we should consider using the even and odd identities, which I had written down in the first video, which are in your notes. So I'm going to rewrite the sine of the opposite of x and the cotangent of the opposite of x, because they're both odd functions, that the sine of the opposite of x is equal to opposite sine x, and the cotangent of the opposite of x is equal to opposite cotangent x. All over the cosine of x equals 1. Now notice here, I'm working with the left side. It's it's the most complicated of the two, because this side is just a single number, but I'm working with the left side. And notice also, I'm writing step by step. I'm showing my work and I'm writing equals to the other side. Okay, now, a negative times a negative is a positive, so of course I'm going to rewrite this as the sine of x times, now cotangent of x, this is where I would use the quotient identity, is the cosine of x all over the sine of x. And that's all over the cosine of x. Well, as you can see here, these are going to cancel because this is like over 1. These are going to cancel. So I have the cosine of x all over the cosine of x is equal to 1. Now, a lot of students will stop right there. I'm not going to stop right there. I'm going to go one extra step, because the cosine of x over the cosine of x is 1. As long as the cosine of x doesn't equal 0, that is. And I have 1 equals 1, which to me shows, verifies, that this is a true statement for any variable that it's defined for, because again, well, of course you can't have 0 on the bottom, but you have to remember here, this is a true statement. A true statement is typically an indication that it works for all real values, that this is an identity. Okay. Now the second one's a little different, because in the second one I have a little bit extra stuff on both sides here. I've got these two rational expressions here involving trig functions, and I've got this expression on the right that involves a product of two trig functions. So I really want to figure out, am I going to work with the left side or am I going to work with the right side? And to me it's pretty obvious to work with the left side, but I've done a bunch of these in the past, so I'm kind of used to seeing this, because I have to get this expression, get common denominators. It's going to take some work, and hopefully it will simplify into this simpler looking expression on the right. So I kind of gave it away, as I mentioned before. I am going to get a common denominator, so I'm going to do a little algebra here. I'm going to write these with a common denominator, which would be the product of the quantity 1 minus sine x times 1 plus sine x. So I would have, if I multiply top and bottom by 1 plus sine x, and then over here, multiply top and bottom by 1 minus the sine of x. So times the top is easy. And that equals 2 tangent of x secant of x. Now I'm going to put them all over my common denominator. I'm going to do something a little tricky. I don't often do this when I have factors in the denominator. I'm going to multiply the factor. Oh, I wrote cosine. Heavens to Murgatroyd. I'm going to multiply these two guys here because they're conjugates, and I get difference of squares. So I'm going to write 1 minus sine squared for my common denominator, because that's what you get if you multiply those. Now I'm going to write 1 plus the sine of x minus the quantity now in parentheses, because I'm subtracting all this numerator, 1 minus the sine of x. Okay. Now I can simplify the numerator because I can get rid of the parentheses, since this is like a negative 1 here that I'll distribute by. And I get 1 plus the sine of x minus 1 plus the sine of x, distributing all over. Now 1 minus sine squared x, if you look back in your notes to the Pythagorean identities, one of the Pythagorean identities that we had was that sine squared x plus cosine squared x is equal to 1. Now that also means that if I subtract sine squared x from both sides or cosine squared x from both sides, I'd still have equality. So if I was to subtract sine squared x from both sides, I have cosine squared x is equal to 1 minus sine squared x. And I'm looking to think that with this denominator, it would make sense to make the substitution in for 1 minus sine squared x. Now if you're looking at that and you say, well, I wouldn't have seen that one coming, well, it just takes practice. You do a few of these and pretty soon you'll start to see some of the same tricks to work in the problem out. So I'm replacing 1 minus sine squared x with cosine squared x. Now the 1's cancel and I get 2 sine x all over cosine squared x. Now look what I have here. I'm getting to the point where I've got to try to make this guy look like that guy. I have the 2, but I need the tangent and the secant. I have sine x in the numerator. I have 2 factors of cosine of x. Watch what I'm going to do in this step. I write this as 2 times the sine of x over the cosine of x times 1 over the cosine of x is equal to 2 tangent x secant x. Do you see how I took the cosine squared x, wrote it as 2 factors, and broke it apart? If I was to multiply this back, I'd get right back to where I started. And I hope you see why, because the sine of x over the cosine of x is the tangent of x, and 1 over the cosine of x is the secant of x. So this gives me 2 tan x secant x is equal to 2 tan x secant of x. See how I get exactly the same thing on both sides? And that's when I know I have verified my identity, at least for all the values that it's defined for. All right, now, my professors, when they would get done in college, when they would get done with a proof, they would write down, right next to it, they wouldn't put a check mark, they would write QED. QED. And I thought, what does QED stand for? And I looked it up, and QED is Latin, quod erat demonstratum, that which is demonstrated. So it shows that which is demonstrated has been shown to be true. So if you want to get a little snazzy, a little fancy, QED, EOP into proof, and you have shown, and again, every step is listed. I might have done a little bit here of basic algebra, but every step is listed. The t-shirt tells it all. You must show your work on these problems so that I can follow the steps. No shortcuts, no jumping from here to here. No jumping from here down to here. Show me the steps, show me the logic. It's as if I gave my wife my key to grade your paper. Now my wife can follow a key and she can understand what to look for by looking at the key, but she's not going to be drawing conclusions that you might draw, that I might be able to draw, and understand what you're writing down, you've got to show your steps. Even though if it takes like a half a sheet of paper to do one of these, that's what you need to do. Because if I'm not following your logic, if there's gaps in it, I won't know if you're doing it correctly in your head and making the jump, or if you're just kind of guessing at it. Because I've had students that'll do that. So be sure to show all your work and write it down neatly, and until you get to the point that you have exactly the same thing on both sides. And then if you want to write QED, that's fine.